All right, ladies and gentlemen, we're going to start talking about titrations and what they are and what we use them for and what math we can do with them in AP Chemistry. Titrations are something that you hopefully all remember from Regents Chem. It's a really fundamental lab technique. You are going to be doing a lab with titrations for me in this unit. And realistically, titrations are fairly simple in terms of the technique is simply adding one thing into another thing and being able to figure out concentration from that process. You can stop the titration once you think you have completely reacted one of your compounds and sort of use the fact that you know the concentration of either the acid or the base to figure out the concentration of the other. That horrible formula, MABA equals MBBB, which we are not going to use in this class because that's our dilution formula and not about acids and bases. It's more sophisticated when we're working at this particular level. And remember, we have the use of burettes, so you have your burette and you're adding something in. And then you can use an indicator, or we're going to be doing some labs where we use pH meters to actually monitor the pH while we're doing the titration. Realistically, it's just a technique to figure out concentration of something. That's fundamentally what titration boils down to. How can we measure amount? It's typical that you put your base in the burette and have your acid in the flask that's underneath it, but it doesn't have to be that way at all. Indicators and some vocabulary terms. There are two important points when you're doing a titration in terms of vocabulary. These things called endpoint and this thing called the equivalence point. The equivalence point is really the most important part of your titration, and it's where you're going to get a tremendous amount of information about figuring out concentration and calculating concentration. The equivalence point, so I'm going to talk about that one first. The equivalence point is the point at which you have stoichiometrically equivalent amounts of, because we're talking about acid-base chemistry here, your acid and your base. Meaning you can boil it down to this relationship that's on the bottom here, moles A equals moles B. That's going to be super important for us because it's going to be a way for us to tell how many moles of each we have at the equivalence point. Meaning if we can figure out moles of our acid at the equivalence point, we're going to know how many moles of the base we have at the equivalence point because they're going to be equal at the equivalence point. But the equivalence point, this point where moles of acid is equal to moles of base, that's not something that we can actually visualize with your eyes, unless your eyes have like magic X-ray specs on them that allow you to automatically quantitatively determine that moles of A equals moles B, which I highly doubt they do. Then we want to use indicators. And indicators are chemicals that will change color in certain pH ranges. And you pick an indicator that will change color around the pH of your equivalence point, because if you know what you're doing, and something that we'll be talking about quite a bit, is what is going to be the pH at the equivalence point. Hence, the answer is not always 7. And so the indicator changes color at what is called the endpoint. Endpoint is simply just a term for when does your indicator change color. That is the endpoint. So by picking an indicator that will change color around the same pH as your anticipated equivalence point, you have a way of visualizing your reaction, and that's really the key point. You cannot see that your moles A is in fact equal to moles B, but if you know what you're doing, once your indicator changes color, that end point of the indicator overlaps with the equivalence point of the titration, and you stop, you make measurements, you say, okay, how much have I added, what's the volume, what's the concentration? From volume and concentration, you can get moles, and you can say that moles A equals moles B. Titration curves. Very typically, information from a titration is graphed into something called a titration curve. I'd like you to sketch this into your notes. It's not hard. I mean, you would look at the axes. There's not an incredible amount of information here. Graph of pH is a function of the amount of added base or acid. Meaning what's being graphed here, what's being plotted on the axes. On the x-axis, we have volume. In this case, it's volume of the base. On the y-axis, we have pH. So this would, in order to create a titration curve, you would need a pH meter that is monitoring the pH of your solution as you are adding more base. So it's basically you add some base from your burette, you see how much base you've added, you see what the pH is, and then kablamo, you have a data point that you can graph. And all titration curves will have this sort of S shape. It's very, very common to have this sort of initial slow, low slope section followed by a very steep portion of the curve, followed by again another low slope section. And in this very particular case, volume of the base, because it's base that's on the x-axis, that means that the base is in the burette, and that our acid is in the flask, because when you're monitoring pH, you're monitoring the pH of the thing in the flask that's underneath the burette. So when we see that we're starting with amount of base added 0, we see that we have a very low pH, which makes sense because all we have in our flask is an acid. And additionally, as we're adding our base from the burette into the flask, we see that the pH is going up, right? We started at low pH and then we're increasing, we're heading up to 14. So we are adding base into the acid and we see an overall increase in pH. Now we're going to talk about the sections of these curves. First up, this portion right here. What's going on right there? From the start of the titration to near the equivalence point, the pH will go up very, very slowly. At this part of the curve, you have more acid than base. You're doing a neutralization reaction here, right? H plus OH minus makes H2O. At this part, this before the equivalence point, we have a very low pH, right? And so we're seeing that the pH is increasing very slowly because we've got more acid. Acid wins. Acid is the thing. The acid that's there is controlling the pH. So the pH is therefore very, very low. Yes, we're adding more base in, but we haven't yet completely neutralized all the acid. There is still some acid in solution. And then we get to this section, this sort of very, very, very steep section. You're always going to see a very rapid increase in pH around the equivalence point. So we'll always have this sort of slowly increasing section and then this super, super steep section. And it's here where basically you're changing over from having more acid to having more base. So this is why the pH increases very sharply. You're switching which one you have more of. And that steep section, the middle point, right there. The middle of the steep section is always going to be where your equivalence point is. And your equivalence point is a very special point. It's probably the most useful piece of information you're going to pull from a titration curve. At the equivalence point, moles acid equals moles base, which is a very, very, very useful piece of information. Moles, and I'm going to specify that a little bit further because I want to be clear, it's going to be moles of H plus equaling moles of OH minus. That steep section where we're going from having more acid to having more base, and that equivalence point is right in the middle of the steep section, that's usually where you're going to glean all your information from the titration curve. The rest of your titration curve, you can do calculations, but they're typically not the point. You tend to be very interested in where is that equivalence point, when are moles acid going to be equal to moles base. At this point, the solution contains only water and the salt made from your acid and base. For now, equivalence points are going to have a pH of 7 because the salt that's going to be left is going to be a neutral salt. But as you know, we had that conversation about salts, and salts can be acidic or basic. So in our next unit, we're going to talk about when that equivalence point, when moles acid equals moles base, is actually not going to be at a pH of 7. So know that the equivalence point is not You don't say, oh, it's neutral, oh, pH 7. Like, no, that's not what the equivalence point is. Moles A equals moles B, amount of H plus equals amount of OH minus. And then afterwards, that last component, now we've shifted over and we have more base than acid. So we have a very, very high pH. We have used up all of our acid is completely gone, and all we're doing now is just adding more and more base into our solution, so the pH is getting higher and higher and higher. Strong acid, strong base titrations. There are many different points in a titration at which pH can be calculated, and we're going to have a look at all of them. Hey, aren't you so excited? First of all, you can figure out the initial pH. And this means really before you have started your titration, before you've done anything, before you've added any of the base from the burette, you have your acid in the flask, you put the pH meter in, you read the pH. Initial pH, that's what I mean. Before you started your titration, what is the initial pH? Then you can start your titration, and you can calculate before you hit the equivalence point, what is that pH going to be? And this is going to depend on how much acid has not been neutralized by your base. So it's about calculating how much acid remains, how much acid is left, and then doing your pH calculations from that. This is not the same as how much acid you have started with, because you've started doing your titration. You've started neutralizing some of your acid, so you've got to figure out how much is going to remain. Then you can calculate the pH at the equivalence point. And this can be done using the fact that moles acid equal moles base. If we're doing strong acid, strong base titration, which is what we're talking about in this unit, we're going to talk about what happens when we have weak acids and weak bases in our next unit. The pH will be 7 at the equivalence point because we've created a neutral salt. And all we have is just water in this neutral salt, so pH is going to be 7. And then you can also calculate the pH after the equivalence point, and that's going to be determined by how much excess base remains. Because at this point you've used up all of your acid. The acid is completely gone once you're after the equivalence point. So your pH is going to be determined by how much additional base you've added. So for example, we can do the first one. That's going to be really quick. This is sample problem number 17. What is the initial pH in the titration of 0.1 molar NaOH into 50 milliliters of 0.1 molar HCl? Well, I think that what's useful in doing all titration problems is to figure out what's in the flask, what's in the burette. And sort of reading this, it says in the titration of 0.1 molar NaOH into the 0.1 molar HCl, which means that when we have our burette and we have our flask that's underneath it, we're putting the NaOH into the HCl, and whatever we're monitoring the pH with, it's going to be measuring here. So we're measuring the pH that's in the flask. And if we look at initial pH, that means that we haven't added any base. Right? No base has been added, which means that we don't care at this point in time that we have 0.1 molar sodium hydroxide if we haven't put any of it into our flask, which means that our calculation is going to be based on this. It's essentially saying what is the pH of 0.1 molar solution of hydrochloric acid. That's really what the math boils down to. And we know that HCl will completely dissociate to H plus and Cl minus. So if I have 0.1 molar HCl, I will also get 0.1 molar hydrogen ion, and I'm looking for pH. pH is the negative log of the hydrogen ion concentration. So all I'm going to do is take the negative log of 0.1 molar, and you should be able to do that without a calculator. Really hopefully you can. Figure out that the pH at this point is 3.00 molar, 10 to the negative first. So the calculating initial pH is very, very straightforward. It's just based on how much acid you have. That's it. You haven't added any base, so you're not concerned with figuring out how much base will remain, how much acid remains.